Good morning or afternoon, whatever time you're viewing this. Hopefully we can get through a little bit of this because I think we might miss both Tuesday and Wednesday class. So let's talk about what we need to for Chapter 10. We're going to start this chapter, and it's really the last information that you need in order to prepare yourself for Stats 2 and also to fulfill all of the objectives that we have for this Stats 1 class. So it's going to be talking about tests of hypothesis. Now we're familiar with the words hypothesis. We know what that means, right? It's a best guess. So in this chapter, we're actually going to be making guesses, and we're going to see how we can not prove them to be true, but show that there's not enough information to say that they're false. That's kind of the difficult bit with it. So we're going to learn about some testing, some procedures, and we're going to talk about different kinds of errors, and talk about test statistic and how that is used. We're going to be talking about the one-tailed and two-tailed hypothesis. That's all pretty simple once we get into that hypothesis mode. And then the actual math part will be to conduct the test of hypothesis about a population mean and compute and interpret the p-value. Push comes to shove, if we aren't able to meet together and really explain this, I will cancel anything about p-value from the quiz for this week. And we'll just talk about the hypothesis testing. So don't be afraid. If we get into trouble, we will make an adaptation, right? So steps of hypothesis testing. I don't know that I need to go over this too much. And of course, my face is right there. So I'm going to move my face up a little bit. Kind of strange to move one's face. There's the 5 steps down at the bottom. And we'll go through those. You can read those on your own. But we are going to go through that procedure as we decide. Notice the down here at the end, when we're finished with this hypothesis testing, we're either going to have do not reject, DNR, it's kind of like do not resuscitate for you health students, or reject. Now, notice we don't ever accept our H1, which is our initial hypothesis. We can just say we're not rejecting it. We don't say we accept it, we just don't reject it. Or we can actually reject it and say that it's not going to be true and accept the H1, which is our alternate hypothesis. Hopefully that'll make sense a little bit later. So we have two different things. The null hypothesis, H with a little subscript of 0, is the statement that we're going to make about whatever it is we're testing, okay? We're saying that that is going to stay true. Then we have the alternate. Well, what if it's not? Then we have the H with a little 1 by it. And this is the way we're going to come up with it. Our null hypothesis is H0, and H1 is the alternate hypothesis. And they are mutually exclusive and collectively exhaustive. Something can't be in both camps. It's one or the other. We always presume that our null hypothesis is true. The burden of proof lies with our H1. So that's why when we do a random sample, it's used to reject our null hypothesis instead of confirm it, because we're always assuming that it is true. And I think a really important part of this is down here. Equality is always a part of the H0, the null hypothesis. That will make more sense, but that is a key in writing our hypothesis. So testing errors, study this as you will. It's just which kind of errors are called. They have different names for them. Not going to go too much into this right now. We need to get into actually setting up our hypothesis. The test statistic versus the critical value. Our test statistic is going to determined from the sample information. We've done this before. And the critical value is the dividing point between the region where the null hypothesis is rejected and the region where it's not rejected. This will look familiar to you because we're going to be using that T and Z score again. And we're going to be drawing our picture and looking at different areas. So we're going to look at the dividing line, reject on one side and do not reject on the other side. That's what our critical value is going to be talking about. Some of these will be one tail and some will be two tails. Sometimes we'll have the whole information in one tail, but sometimes it will be divided between two. Notice when we divide it between two, it will be when we have that equal sign in our null hypothesis, where it's yes or no. Then we're going to be dividing it equally. If it's greater than or equal to or less than or equal to, we're going to be in one tail or the other for that hypothesis. Here's some symbols and what they mean. Sometimes word problems get a little tricky, as we know. We have talked about some. And this chart is good to refer to when you have a word problem and you wonder which way to draw your null hypothesis. And this is what they look like. Okay, this page is confusing without us working on it together, but what it is saying is that sometimes we have them equal to each other. Our null hypothesis is equal, so our alternate hypothesis is going to be not equal. Here we have greater than or equal to for the null hypothesis, and our alternate hypothesis will be the opposite, right? It'll be less than. Here we have the less than and equal to, and our alternate hypothesis is going to be greater than. Notice equals is always part of the null hypothesis. The rest of this we'll explain a little bit later, but that's the critical part, is how we write these things. So here we have our first problem, and I'm going to just stop the recording for a minute and reset so you can kind of take a breath. Okay, let's look at this problem. Don't be alarmed if you're not able to figure out how to write these hypotheses right away. It's the first one, right? So here we have a furniture manufacturer, and they produce this certain model, and they are wondering, here's our information about it, a mean of 200 and a standard deviation of 16. They started some new production techniques, and new people have been hired, and they want to see if there is a change to the weekly production. In order to check this, I'm not used to doing this at home, so I have all sorts of distractions. In order to check this, they're going to set up a hypothesis and an alternate hypothesis. Remember, the hypothesis is the one that says the equals in it. So a sample from last year's weekly production, we have a mean number of deaths produced at 203.5. We want to test this using the 0.01 significance level. So we have a lot of numbers right now. So how do we set up our null hypothesis, our alternate hypothesis, and then test? Let's look at it. First, we're going to state the null hypothesis, which is no change. Remember, null hypothesis is always status quo. Whatever I'm trying to prove, the burden of proof is with the alternate. Sometimes it's easier to actually write the alternate statement first. In this case, it would be that my mu is not equal to 200 for the alternate. Mu is equal to 200 for my null. Okay, so this wording goes with this kind of setup. I think that's an important thing to look at what the words are. Then we are going to select the significance level. It was stated in the problem, 0.01. And we are going to use a test statistic. Since we know, it's the same thing we were doing last week. Since we know our population standard deviation, we're going to use the Z distribution. Okay, now what do we do with that? Here is a nice little formula for you. Since our Z distribution is known, we are going to use, our standard deviation is known, we're going to use a Z distribution. And Z is going to be equal to our sample mean minus our mu, we've done this before, over the standard deviation divided by the square root of our sample size. So make sure you can identify all of these parts. Let's look and see how this works. Since it's an equal or not equal to, we are dividing into the two tails, right? This is going to be a two-tailed problem. So when we compute that value from the last page, I'm going to go back. When we compute that Z, that is going to be where my critical value is. What this is saying is, I'm rejecting if I'm way over here, and I'm rejecting if I'm here. When I do the math, I find out that my critical value is here. So do I decide to reject or to not reject? Well, let's look at it again. Where is that critical value? It is in this do not reject area. If that red line, if the total for my Z from the last page, going back one more time, when I solve that and get a number, if I find that that is over here in my reject area, or way down here as a negative in the reject area, then I would conclude that I would reject the null hypothesis. Doesn't necessarily mean that the alternate is true. It's just that I've rejected the null hypothesis. Notice this is just how I find my level of significance, okay? So we have 0.01. I have to split it into two pieces. So my inside amount is going to be a 0.98. Half of 0.98 is going to be as close to 495 as we can get. And that's where I came up with 2.04. 2.58. Let's just go back. 2.576. When I do the math, I get 1.55. Okay, and that was right here. It is not over here in this region. This number I got from my z-chart, doing my level of significance. I'm going to go back. Okay, using that level of significance, I get my, they carried it out a little further than our chart shows, but as close as we would get, it would be 2.58, right? They have 2.576. They have a chart that's a little fancier than ours, evidently. That's what their area is here. This is just from the significance level. This is not doing math with any of our numbers. When we do math with our numbers, we get that 1.55. Okay? Again, they computed it to a different decimal point. This is what we would get. It is still in this area of do not reject. So the conclusion is that 1.55 falls within the do not reject, so we do not reject it. We're going to say that the population mean has not significantly changed from 200, even with those added manufacturing techniques and the new employees. Okay, let's look at one more. On this one, we're using the same little bit. We are just going to look at this different example. Okay, we're still talking about our desks, and we still have the same significance number. Suppose in the previous problem the Vice President wants to know whether there has been an increase in the number of units assembled. To put it another way, he's not looking at an equal or a change. He wants to look at an increase. He wants to find out, using these other production methods, that the mean number of desks assembled in the last 50 weeks was more than 200. We still have the same basic facts here, but what are we going to use now for our null hypothesis and our alternate hypothesis? Let's think. This time, we're trying to prove that it's more than 200. Remember, burden of proof is with the alternate hypothesis, so this one is going to say my mu is greater than 200. The equal sign always goes with the null hypothesis, and it's going to be the opposite, right? So it's less than or equal to 200. We're looking for an increase in our change. Okay, so this is going to be a one-tail, because we actually are trying to prove that something is greater than. Okay, we have the same level of significance, and we're going to use the z-distribution again. So instead of it being a two-tailed test like we had before, where we had it split between the two sides because it was an equals, we are actually all in this area because we're trying to prove we will reject that it stayed the same. We'll reject the null hypothesis if I can prove that it is over here in the area of reject, okay, over in the region of 0.01. How do I find that critical value of 0.01? On the z-chart, right? How much information is being held there? 0.01 is what I will be looking up at the chart, and I hope I have a chart here. No. Let's see if it is in that other chart. It'll make you all dizzy. Okay. We're looking for 0.01, and it looks like it's way up here at the top, isn't it? 0.01. Evenly between these two, which is 0.02 and 0.03. Let's cruise down here. Okay. So when I am not splitting it up, I have the entire 0.01. Okay, I did that completely backwards, right? I have to take it away from 50, so I wasn't even thinking. It's the trouble when I'm not at my board, right? So if I'm measuring, I'm subtracting 0.5. I'm subtracting from that 0.01, which will give me 0.49, which when I look it up on the chart, 0.49, it is going to be over here, right there, right? 2.33. Move down here a little bit. 2.326. Again, they have a fancier chart than we do. So that is our critical value, and this is the area of rejection. Okay, because we only have it in the one tail. All right. When I do the math then, I do the math to compare it with this critical value that I got from the z-chart. When I do the math,